Hi class, we're going to continue our study in chapter 2 here, and we're going to move into section 2.5, which is to talk about deductive reasoning. Excuse me. So we have two objectives in this section. The first is we want to review conditional, converse, inverse, and contrapositive statements. We'll do a quick like P and Q and in words and talk about those. And then we're going to understand and use two laws of deductive reasoning. So first is called the Law of Detachment, and then the second is called the Law of Syllogism. All right, so first off, let's go back and talk about how you write related conditional statements. So I'm going to start with the conditional statement. And what you're given is a hypothesis, P, it is raining, and a conclusion, Q, it is cloudy. So how you write it, it's P implies Q, or if P, then Q. All right, that's another way to write it. And how you would say it, if it is raining, then it is cloudy. So the converse is you switch the hypothesis and the conclusion. So it's Q implies P, or if Q, then P. So that is, if it is cloudy, then it is raining. The inverse, what you do is you negate the hypothesis and the conclusion of the original conditional statement. So it would be not P implies not Q, or if not P, then not Q. So if it is not raining, then it is not cloudy. The contrapositive is you negate the hypothesis and conclusion of the converse statement. So you flip the P and Q and you inverse them. So it's not Q implies not P, or if not Q, then not P. So if it is not cloudy, then it is not raining. So those are just starting with the conditional, converse, the inverse, and the contrapositive. All right, so let's do an example of writing conditional statements. So you're going to use the given conditional statement to write the following, okay? It's converse, it's inverse, and it's contrapositive statement. Then write each statement in symbols as you've done for the given statement. So here's the problem. If a number is a whole number, then it is an integer. Okay, so this is going to be our P right here. Number is a whole number, and our Q is it is an integer. So the converse, we're going to flip it. So the integer part is going to come first. So if a number is an integer, then it is a whole number. So we started with P implies Q, and now it is Q implies P. All right, let's do the inverse. So again, we had if a number is a whole number, then it is an integer. So the inverse is if the number is not a whole number, then it is not an integer. So you're just negating both the hypothesis and the conclusion. The contrapositive, all right, is the inverse of the converse. So if a number is not an integer, all right, then it is not a whole number. So the integer was the Q part, so we're saying not Q implies not P. Apologize for the coughing. While I'm recording this video, I'm a little sick, so forgive me. All right, let's move into deductive reasoning. So deductive reasoning is the process of proving a specific conclusion from one or more general statements. The thing about deductive reasoning is a conclusion that is proved true by deductive reasoning is called a theorem. So the important thing about deductive reasoning is that it proves a very, very specific conclusion, not a general conclusion. All right, so we've talked about inductive reasoning too. So inductive reasoning is observing patterns or examples and then using them to form a general conclusion. But the thing is that general conclusion may or may not be true. All right, deductive reasoning using known information that we know is true to write a logical argument that arrives at a specific conclusion that is true. All right, this with deductive reasoning is how we prove theorems. All right, so let's talk about the law of detachment, which we'll use. So if you have a statement, so if P implies Q, so if P then Q is a true conditional statement. So we're saying it is a true statement. And P is true. So we know that P of this, sorry about that, we know that P of this complete conditional statement is true, then Q must also be true. So if P is true, then Q is also true, right? As long as the entire statement is a true statement. All right. Let me give you an example. So using the law of detachment to make a true conclusion. All right, assume that the first statement, all right, in the P implies Q is true. So if you shop at Save Market, you will save money. So if you shop at Save Market, then you will save money. If we assume that the P is true, right, our conclusion is that you will save money is also true. That's what the law of detachment is saying. If you have P implies Q is true, and we know P is also true, then the second part Q must also be true. All right, so let's do two other examples. So determine whether each reasoning is valid using that law of detachment. Right? Assume that the first statement in P implies Q is true. All right, so we got two examples. If a student gets an A on the final, then the student will pass the course. Right? So what we're testing to see if the reasoning is true, Leo got an A on the final exam, so he will pass the course. The second thing we'll look at, if two angles are adjacent, then they share a common vertex. So if angles 1 and 2 share a common vertex, then the angles are adjacent. All right. What do I mean by determine whether the reasoning is valid with the law of detachment? If a student gets an A on the final, then the student will pass the course. All right. Leo got an A on his final, so he will pass the course. In symbols, the first sentence is a true conditional statement. The first part of the second sentence, all right, is also a true hypothesis. So what I mean by that is Leo got an A on the final is also true, right? Thus Q, right, if A is true, then Q must also be true. So thus Q, the second part of the statement, is true, and the reasoning is sound. So the argument is valid. All right, but let me show you an example where the argument is not valid, because I can understand how this can be a little confusing. All right, if two angles are adjacent, then they share a common vertex. All right, so if angles 1 and 2 share a common vertex, then it must be that the angles are adjacent. All right, in symbols, the first statement of the conditional is true. All right, so two angles are adjacent. But the second part of the true conditional statement is not true, which is they share a common vertex. All right, so if you look over here, I have angles 1 and 2. They share a common vertex, right? But they're not adjacent angles. Like angles 1 and 2 are not adjacent angles, right? Because they don't share a common side. So the argument is not valid, right? And this is being because you can look at the second, the second argument is not contingent on the first argument. So what was said first does not necessarily automatically make what is second is valid. All right, so the law of syllogism, if we have P implies Q is true, all right, so it's a true statement, and Q imply R is also true, then notice how the ending point here, Q, and the starting point here, Q, are the same. If both of these statements are true, then P implies R, or if P then R, is a true conditional statement as well. All right, let me give you an example of this. So I want to use the law of syllogism to form a conclusion that P implies Q. So here's what I'm given. Given a figure is a square, then the figure is a rectangle. That's one statement. All right, that's my P right here is figure is a square, and my Q is a rectangle. Then if a figure is a rectangle, that's Q, then the figure has 4 sides. That's my new R. So if P is a square, implies Q, that's what that statement is saying. All right, that's a true statement right there. And then if the figure is a rectangle, that's my Q, implies the figure has 4 sides. That is also a true statement. So both P implies Q is true and Q implies R is true. Well, then it must be P implies R, it must also be true. So if the figure is a square, we knew it was a rectangle, we knew this was a rectangle, then the figure has 4 sides. So thus we can say that P implies R is true. All right, another one. Using this law of deductive reasoning and syllogism here, all right, we'll use both law of detachment and law of syllogism, excuse me. Decide what you can conclude from the true conditional statements given. And note whether your reasoning involves the law of detachment or the law of syllogism. All right, so let's think about this. I got 2 statements. All elephants are mammals, and all mammals have hair. So let's see what I'm talking about here. All right, the given statements are true in the form P implies Q, all right, all elephants are mammals, And all mammals have hair, so Q implies R. That's also given to be true. Well, look what I have here. I have P implies Q and Q implies R. The Q's here are the same. So what we can conclude is that all elephants have hair. That P imply R is then a true statement. And what we used here is the law of syllogism. Let's do another one. Again, decide what you conclude from this true conditional statement. All right, and then talk about if you use the law of detachment or the law of syllogism. If a number is prime, then it has exactly two factors. All right, the number 11 is prime. So what can we conclude from here? All right, the given statements are true in this form. P implies Q. If a number is prime, then it has exactly two factors. And the other statement here, all right, if a number is prime, yep, 11 is prime. That's also a true statement. So think about this. There's no secondary statement that's like Q implies R. But I'm saying this is a true statement. And the first part of it, P, if a number is prime, the number 11 is prime, that is also true. What we can conclude is that the number 11 has exactly two factors, that it has exactly two factors, and that is that Q is true. That second part is true. That's the law of detachment by saying, look, if P implies Q is true and P is true, then Q must also be true. All right, class, thanks.